thank you for invitation to this nice conference. And as I was asked by the organizer, I shouldn't talk about things I have talked, in this philosophy of physics and cosmology meeting. So I tried to find a new angle to address similar questions. And the first question, I think it was a nice introduction yesterday. We had some homework to do. And I asked myself yesterday, so what is cosmology? Usually what I say to people, this is what I do. Okay? It's not a joke. I think often in science, you don't have to wonder too much about what you are doing. You just do it. And then you let historians and philosophers try to clean all this mess. But we have to go sometimes to work with badly defined properties. I mean, we are used as physicists to work with badly defined mathematical theories and concepts. And I think this is what is important, is we do something out of that, and later on we clean up if it looks like it is working. The second thing about this is remind me a very old story which happened, actually, this is a true story, which I often tell when I do popular science talks, and it's related to my first visit to Cape Town in 2001. I was visiting George, and there was a small cosmology meeting in Cape Town, and when I arrived at the airport, I had to cross the border, and I was asked, why are you coming here? And I said, well, I'm coming for a cosmology conference. And the guy asked me, and do you have some samples? Then I was thinking, okay, cosmos, you learn cosmos chaos when, you read books about cosmology and the Greeks. Then, of course, I realized, yeah, this is obvious. I mean, cosmology, cosmetics. And so I went to a dictionary and I look, and yes, cosmos has another meaning. Cosmos was the name in ancient Greece of the jewels that women had, so the very beautiful jewels. And what I learned from some friends who are teaching Greek, they told me, yes, this is, Pythagoras, this is a legend, chose this word because he wanted to give to have a feeling of the emotion you get when you look at the night sky. So that was the first meaning. And actually, recently, there was further development on these stories because I was discussing with a friend of mine who is teaching Greek at La Sorbonne, and she told me, there is a third meaning to this word. I say, yeah, which one? According to Pythagoreans, this is the highest quality of a woman. So I say, so what is it? And she told me, this is silence. So maybe this is what cosmology is about. Just look the sky and don't talk too much, and just enjoy what's the beauty of the night sky. And for me, who has been mostly a cosmologist, but I've been growing as a general relativist. I think what is important when you look at the history of general relativity, and soon we'll have the 100th anniversary of Einstein's paper, is that if you look at cosmology, it was like a space of freedom to think general relativity. And I think today cosmology is also a space of freedom for us to think about quantum mechanics in different settings. And I think this is very important to have this space of freedom where you can almost, start to very bold theories and ideas. And it reminds me that Papa Petru, so the relativist Papa Petru, was always saying that cosmology is a sport. So maybe this is why we are allowed to do many things. Okay, so we had many talks about what cosmology does for us, and in particular, I think, and this is a point that I completely agree with Joe Silk, I think there is more than just large-scale structure, because over the past decades, we have learned a lot about the history of the matter of the universe. We understand why, starting from pure neutrons and protons, we have all the chemical elements that are here today in the universe, that we observe the whole Mendeleev table. We can explain the origin of all the elements of the Mendeleev table, and I think this is a big success. If you are asking about the origin of matter, you know that starting from neutrons and protons and this Big Bang model, you will get the situation where you will synthesize all these elements. As I told you, I'm doing general relativity most of my time, so I'm a physicist. What I like to do is to start from what we know. What I will say by what we know, what we can test, what we can experiment, which means that all these things, they have a domain of validity. And out of that, we just built up theories, models, and they all have this domain of validity. And I think this is... as a theoretician, I think this is the most important thing. The theory is a good thing. The domain of validity of the theory, I think, is an also important point of what we have to learn and also what we have to teach to our students, because most often a lot of people think that these laws are like, golden rules that are written somewhere. And we know that we will have to change them because we try to extend the domain of validity by doing further experiments and further observations. And when we start from this model and this theory, usually what we like to do is to extrapolate them far beyond the domain of validity where they have been tested and try to see where we get into trouble. Sometimes we get into trouble with experiments. Sometimes we get into trouble because there are other extrapolation and this collides. And when it happens, well, we have to try to solve them, and this is a way we can progress in our way of thinking to these theories. And then after that, well, we have a way to give some credence to some driving principles in these constructions. And there is no reason for that. I mean, this is just experiments that tell us that this kind of principle have been fruitful or not. And the question would be that when you build these mathematical theories of physics, you have these models, and you'd like to know which one will survive when you go to the next stage, and which one will disappear. And we had many examples in the history of physics where we have structures that has been forgotten or that we are not good enough for going to the next stage. So this is history of physics told us that there are actually no absolute structures in physics, and we have a large freedom in the choice of the mathematical structures to formulate physical theories. And the only thing we can do is that, in the end, the choice we are making, this free choice of the mathematical structure we are using to write down a physical theory, they are just validated by experiments and by the fact that the theory is consistent. There is no other rule. So if you have to change, just change it. And also, we know that sometimes different mathematical structures of formulation can represent the same physical theory. We had some example in quantum mechanics. So it's very interesting to try to know if we can write things in a different way. And this is what I will try to show you a little bit later. At each step, what we realize is that there are some properties that are completely free. It's maybe the topology of space today. The number of space dimensions is also a free parameter. In some theories, like string theories, this is something which is fixed. And I will take two examples. So I will discuss, is it here? Yes. The signature of the metric. So when you do special relativity or general relativity, this is an important property that you give to the metric. And I will discuss about fundamental constants. Both of them actually are related to a principle that I like a lot, which is very important to me, which is the equivalence principle. And I think this principle, which is tested at the level of 10 to the minus 13 today in the solar system, we have no reason, we don't understand where it's coming from. And there is, it's a purely empirical principle, and there is a good reason to think deeper in the validity of the equivalence principle. Okay, so as I said, and George alluded to that in his talk, when you want to make representation of all the knowledge we have, he told us that you have this hierarchy of physical theory, starting from the deepest one to the higher one. And what is important is that these structures are organized in a very interesting way. They are kind of modules which are interacting together. And George gave the example of nuclear physics and atomic physics and blah, blah, blah. I don't remember the whole list here. But what is important is that when you do nuclear physics, most of the time you don't need to know anything about string theory. There is this kind of decoupling between the different levels. They interact together, but they are independent enough that you can do physics. Imagine that to do atomic physics, you need to understand string theory. You will not even start to do atomic physics. And so it's very important in terms of the history of physics, because just from a pragmatic point of view, we started to do low energy experiments and then high energy experiments. Then we are building what we call effective theory, which means theories that are a good description of nature in a domain of validity which is under control. And we have to consider that they are successful explanations at this level of complexity, and they are based also on the concepts that appear at this level. For instance, if you do nuclear physics, you will use protons and neutrons. You don't ask yourself the question, what is neutron and protons? If you ask the question, well, you have to knock on the door of someone who is doing QCD, and he will explain to you what is the structure of a neutron in terms of quarks and so on. You can even try to knock on the door of your colleague and ask him, how do you compute the mass of the proton? Because for a nuclear physicist, this is a fundamental constant. In principle, I should be able to compute the mass of the proton in terms of the mass of the quark, the QCD energy scales. In principle, because in practice, no one is able to do this computation. So I think this is also something which relates to philosophy, because at some stage, we take things for granted. We work with them, and then we would tonight, why are these things that we are manipulating? Maybe you have a colleague that can answer the question, maybe not. And in cosmology, well, we are this problem of origin of the universe. There is no colleague trying to, I mean, the nearest colleague is a philosopher, so this is probably why we are here all together. Okay, so if I look to cosmology, and we have been told about the cosmological model, there are mainly 4 hypotheses. One is an hypothesis on the theory of gravity. We assume it's well described by general relativity. We make an assumption of the matter in the universe. So we take all the fields of the standard model of particle physics, and we are called dark matter and the cosmological constant. But this is not enough. These are theories. We need to find solution of these theories. They are too complicated, so we have to do some assumption to simplify them. So we make symmetry hypotheses, like the Copernican principle. And even then, some properties of these models are left undetermined, like the global structure of the universe. And what is important is that this is a very good model in the sense that it reproduces almost all what we know from the universe from about 0.1 second after the Big Bang to today. So it's a huge amount of time. Okay, so here is a summary of the Big Bang model. So we are here, and we have been told about this later phase. So this is where the physics is in principle known. I mean, there are baryons, there are these dark matters that we describe in some way, there is gravity. But we have the system become complex and highly nonlinear, so this is why we have to use numerical computations. But for a big part of the history of the universe, you can just use known physics and linear perturbation theory. And it works pretty well to understand the CMB, to understand what's happening with, in the primordial universe, like Big Bang nucleosynthesis. And basically, if you change anything in this model, before 10 to the minus 3 seconds, you can see some signature on some observables. And then, of course, you go deeper and deeper, more primordial and more primordial. And this is where you go further and further to what the theories that you have been tested in accelerators. Just to remind you here, we are typically at an energy scale of 100 or 1000 MeV. So it's a very small energy compared to what we have been testing at the LHC. So an example about one of the things George was telling about small universes. So here, imagine that you have an Euclidean plane. You can always cut off a rectangle and identify the shape, so the border, you will get a torus. The question to know whether this property is observable or not depends on the relative size of this universe compared to the size of the observable universe. And you have 2 solutions. Either your universe is much larger than the size of the observable universe, and you are most unlikely to see any signature of the fact that you have these periodic boundary conditions, or it's much smaller, in which case you can find some signature of this topology. And I guess in your numerical simulation, you have also like this kind of boundaries. It will be nice to see how you can give that to someone who doesn't know about the boundary condition and to reconstruct them. So a way to do that, imagine you take, so this is, I think, a truncated dodecahedron, so a 3-dimensional compact universe, and these are the worlds which are identified together. And when you open, because light is going around the universe, you will see many copies of the same galaxy. And you see, this is what an observer lying in this unique galaxy of this universe will see. He will see a sky which looks like it's an infinite space, I mean, covered with many galaxies. Just imagine that you put like 100 or 1000 galaxies in these things. It will give you something which looks like a galaxy catalog. So how far can we see? And I think the best object we have to test the universe on very large scale is a cosmic microwave background. Here is the observation by the WMAP satellite. And when you have this temperature field, you can decompose it in spherical harmonics. You get the ALM, which are the coefficient of these developments. And if the space is isotropic and homogeneous, then the 2-point correlation will reduce to a pure diagonal. It will be a pure, you will just have the CL, which is the angular power spectrum. If you break these 2 hypotheses, you will have off-diagonal correlations. So you can try to take this information into account and ask yourself, how far beyond the size of the observable universe can I see? So this is an exercise we did with a student of us, Ophelia Fabre. And you see this is the size of the universe in units of the size of the observable universe. And this is 1. And so you see, basically, you can see 10, 15% larger than the scales of the observable universe. Scales which are larger, they enter in your computation of the CLs and so on, but their contribution is so small that you cannot actually probe them. But for scales which are 15, let's say up to 15% larger than these physical scales, they have an influence on some of the observations, and in particular, in the correlation of the off-diagonal terms of these matrices. So you can try to go and look for them, but for larger universe, it's most likely that you will not be able to test this hypothesis. Okay, so then Hofer talked about the dark sector, and I think each time we have such a problem in cosmology, we have three options. Either it's an astrophysical problem, which means we are adopting the data. This is what was done at the beginning with supernovae data in the early years. Either it's a cosmological issue or a physical, something about theoretical physics. What is interesting is whether it's cosmological or physical, it means that you need to introduce new degrees of freedom in your cosmological models. And they can be of two origins. Either they can be geometrical degrees of freedom, which means like the Friedmann spacetime is too simple as a background spacetime. And this has been investigated by all people working with Voigt's model, the Mantle-Medmondi models. Or you have new degrees, physical degrees of freedom. And in that respect, I think that if we take this route, and this is the one that Hofer alluded to in his talks, whether it's a modification of general relativity or new matter, it doesn't matter, actually, in some sense, because you need new degrees of freedom, new fields in your theory. The question is, how do they couple to the standard matter fields? Are they minimally coupled, or do you have interactions with them? And this is in the way that you make a difference between a modification of general relativity, which means that you have a new force, which is a long range and not screened, compared to a new matter fields. So for instance, sometimes you hear that instead of taking the Ricci scalar for the action of gravity, you take a function of the Ricci scalar. Well, if you do that, actually what you are doing is you are adding new degrees of freedom. They are scalar degrees of freedom, one more scalar degrees of freedom in your theory. So this is also a new kind of matter, a new field in your model. Okay, so now I arrive to these things about the Lorentz signature. So this is based on the work we did with my friend and colleague Shinji Mukoyama from IPMU in Tokyo. And we were just discussing about physics and causality. And each time we were thinking about that, we were just thinking, well, the best way to implement causality in any relativistic theories is to use the Lorentz metric. And this is what you do if you want to write electrodynamics, which is you use Maxwell theory with a Lorentz metric in Minkowski space. The question is that, do you need to do that, or can you just change these things? As you know, space and time, the representation of space and time has evolved a lot in the past century from the Newtonian space-time description in Newtonian physics, in which you split, you have a clear notion of what is space and what is time. So our space-time is just a bundle of the real axis and the three-dimensional space. And in these settings, you have a lot of things that sounds natural to us, to our intuition, like simultaneity, that coincidence. And and you have also a lot of prediction. And one of the reasons that you have to doubt this picture is from experiments, because according to Newtonian physics, if you go from this point to this point, a space-time position to this one, by different route, and you have clocks which are good enough, you will not measure the same travel time. And this is in contradiction with this assumption. So then you come to this description of special relativity. And in this case, you will introduce a metric for the Minkowski spacetime, which has a signature minus plus plus plus. And it allows you to make differences between different kinds of interval, which are time-like, space-like, or null. And the null interval defines for any observer the light cone. And this is the basic object that you have to deal with in special relativity, because it tells you about causality. And also what is important is that any observer, there is one single thing that you can measure as an observer, is your proper time along your own world line. Just comparing time between two observers becomes really messy. You have to explain how you compare your clocks. So this is special relativity, and when you include gravity, you end up with general relativity, which are basically the same structure locally, which means that we have different light cones. The only thing we know is that if this observer sends a photon, it can be captured by another observer here. They can communicate. Sometimes they can't communicate, and we have appearance of horizons and things like that. But again, the metric has the same signature. So can we try to play with a signature which is not minus plus plus plus? Well, we know from the literature that there have been attempts to that, and Jim Hartle with Stephen Hawking and Gary Gibbons, they have this Tinelin metric for a purely Lorentzian space-time to space to a Riemannian space-time. Eddington in '93 asked himself whether you can use the minus plus metric, and there have been many arguments that it was creating a lot of problems in terms of energy conservation. So what I would like to do is to say, okay, let's try to forget about the Lorentz metric, and let us start with a purely Euclidean four-dimensional space. And let's see whether we can see something like a Lorentzian dynamics emerging on a small patch of this four-dimensional space. Okay, so this can be interesting to discuss singularity and maybe for some other issues. So let's start with a simple example. Just take a scalar field. This is the action of a standard scalar field. So here is the Lorentz metric. And if you vary this action, what you get is a Klein-Gordon equation. And you see, because of this metric, what you get is this kind of operator, the Dalmatian operator. And this is an hyperbolic equation. So you have a time evolution. You will set initial conditions, and it will tell you how the field evolved. Now imagine that, so this dynamics is related to the fact that you have a minus sign here, which reflects in this minus sign here. So now imagine that your metric is just the delta mu nu metric, so here in Cartesian coordinates, which means that the signature is plus, 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 plus. If you try to look at the invariance you can construct with your scalar field, well, you have the norm of the gradient of the field, the potential, and if you try to mix them in any way you want, and you vary your action, you will always get elliptic equations. So there will be no kind of evolution. You will have configuration which will be determined by boundary conditions. So it's too poor to get to something which looks like a dynamics. So what we have to do is we have to add a new ingredient. So what can we add? Like always in theoretical physics, the only thing we know to work with is our scalar field. So let's just add a scalar field. So we add a scalar field, and I will just assume that the Lagrangian of this scalar field is invariant under shift symmetry, like that, and that it is allowed to couple to all other fields. Just because I have this symmetry, by construction, what I know is that whatever the action is, if I vary, it will reduce to the conservation of a current. So let's try to take, to construct such a theory, and now we take because I ask the action to be invariant under shift symmetry, I will always be able to work with the gradient of the field. Imagine that there is a patch of this big four-dimensional space in which the gradient is constant or almost constant. Then I will be able to single out this. It will give you a preferred direction in my space. And so I will define it this way. So this is a unit vector. From this unit vector, you see, I can just define a t coordinate. It's not time because, look, this is always a Cartesian metric. Okay, so I've not cheated here, not already. So I single this direction, which is related to the direction of this gradient of the field in the four-dimensional Euclidean space. Then now I try, so here is an example. This is a configuration of my field. You see this is iso field surfaces. And you see in this patch, well, the gradient is almost constant in that direction, while here it's almost constant in that direction, and so on. Okay, of course, it's not exactly constant, and that will play a role, of course, in your model. So now assume that it is interacting with your initial matter field, chi, and I just put the simplest term I can construct like that. And I take the action in which I have my invariance, so the norm of the gradient of my field, the potential, and this new interaction term. Okay, so this is my action in the on the whole four-dimensional space. And now I want to reduce this action on what it looks like on the small patch m naught where the gradient is almost constant. So this is a small exercise. You just develop everything. And because this is phi is along the direction I call t, this will give me this term only. And if I recombine everything, this action, when reduced just on this small patch, is exactly the action of a scalar field in the Euclidean spacetime. Okay, so for an observer that will be in this patch, he looks at this scalar field, and its dynamic is the same as the one with as the dynamics, a Lorentzian dynamic with this metric eta mu nu. So what is interesting there is that you start for a four-dimensional Euclidean space, and then you allow a coupling to this field that I call a clock field for obvious reasons. And when reduced on this small patch of your four-dimensional space where it gets some kind of a wave, then you have the feeling, the illusion that the scalar field propagates in an effective Minkowski spacetime. So this is a very local property, but you know there is no notion of time because everything is Euclidean from the start. Then what is interesting, so it works easily for scalar fields, and there have been some similar ideas in the literature. What is interesting is that you can generalize that to get a consistent theory, at least at the classical level, for vectors. Even for spinors, it was very difficult to construct Majorana and Weil spinors, and you need that if you want to formulate the standard model of particle physics. And it always requires this interaction with the clock field. So basically, in a flat space-time, you can construct the equivalent of the whole standard of the standard model of particle physics at the classical level. Okay, I'm not bold enough to talk about quantum mechanics in this setting, not yet. So the next question is, do you get something close enough to general relativity? Well, this is possible, I think. So you try to get, so you start from an Euclidean metric, which I call GE, and you try to consider the most general action, which has shift symmetry and which is second order, gives second order equation of motion for this scalar field. And it has been known for more than 40 years. This is called the Horndenski action. And you have many terms. So these G4 are free function of XE, which is the norm of the gradient of this scalar field. And now you just pick up the one which has a shift symmetry, which are second order, and you are left with this very generic Lagrangian. And now what you want to do is you take this action, so it's a purely technical and messy part of the computation, which I will not expose to you, and you reduce that to the part of the spacetime where your gradient is almost constant, and what you get in the end is this effective action now for a metric which has a signature minus plus plus plus, in the same way as we get it for the scalar field. And you see this is the Ricci scalar, but now there is a kind of function which depends on this x, which is the norm of this scalar field. And you have extra terms. Okay. So what is interesting is not general relativity, but it's very close to general relativity. It looks like some scalar tensor series plus fields which are plus matter fields. Interestingly, if you go to the cosmological setting, this P of x acts almost exactly as a cosmological constant or a quintessence kind of field. And so you can make a dictionary between the metric, the Euclidean metric and the effective metric on the small patch M naught. So when we got that, we were very surprised because I was thinking that you can kill this kind of idea from very, very fast. And actually you can even, at the classical level, you can get something where you have a theory of gravity which can be close enough to general relativity and on which you can formulate vectors, spinors, and scalar fields. Okay, but you see, because I have these kind of couplings here, what you will get as an output of this theory, as a kind of prediction, is that the gauge coupling of your interactions will be space-time dependent, and this is very well constrained. Also, if you look at the propagation of the gravity wave, so the perturbation of the G matrix and the propagation of light, so of the vector field, don't try to understand these formulas, they are just pictures. They are not the same formula. This is the thing important. So which means that the speed of propagation of gravity waves and of photons will be completely, will be different. So you will have two different light cones. This is not a problem in general, as long as they are not degenerate, which means completely open. But you have constraints on that, because if photon propagates faster than the gravity waves, then you will have some kind of Gravier-Cherenkov radiation. And in particular, so you have three functions here, and they have to satisfy, at least in the patch where we are supposed to be, that this kind of constraint. And you see this is a very tight constraint for these two speeds. Okay. So I think it's an interesting idea, is that maybe if we have a problem with time, we can just come to forget about it and try to reformulate everything. Of course, we don't have any quantum theory, but we have some idea of how to do that, maybe in another meeting. And it can raise some interesting ideas. For instance, singularities. Like the Big Bang singularity can be seen as a topological defect in this scalar field instead of a pure singularity. So maybe you can go from one patch of one pocket of the universe, we have a kind of time directions, to another pocket with another time direction. Okay. I have 10 minutes to tell you about fundamental constants. So I've been working 15 years on fundamental constants. And the reason was that 15 years. In 1999, John, were you on the paper? So John is almost responsible for that. There was a paper by, it was John Webb and collaborators, so you were one of the collaborators, who was claiming that the fine structure constant was smaller in the past. Okay, and I was a postdoc at the time. I was reading the paper and I say, what the hell? And I never thought about it. So I started to discuss with people and to look at the literature. And I came back on all the work by Dirac and many people on deviation from general relativity. And, well, I concluded that, as many other people did before me, that it's a very nice way to test the validity of the equivalence principle that you can generalize on astrophysical scales. So I tried to study more fundamental constants, and the more I was studying them, the more I found they are really interesting to understand both the history of physics, the structure of physical theories, and also general relativity. So, well, they are interesting because whatever you do when you want just order of magnitude, you manipulate fundamental constants. And this is related to all this fine-tuning argument that if we change some parameters by a factor 2 or 3, then the physics will be completely different. Joe gave an example to get the typical mass of the stars. He didn't have to write down pages. Just by basic order of magnitude, you were able to derive the typical value of the mass of the star. More important, and this I discussed before, is that these fundamental constants, they characterize basically the domain of validity of a fundamental theory. And this is important because they signal you. When some values become of order unities in unit of some constants, usually you start to run into problems. Like when V over C becomes of order 1, you know that you cannot use anymore Galilean kinematics. You have to shift to relativistic kinematics. So the question is, how do you define a constant if you may allow them to vary? Again, I was faced with a question by one of my first popular science talks, the title of which was Are constant varying? And I was thought, so if constant varying, have you looked at the dictionary? And I was running into a problem when I looked at the dictionary. So then I decided to define a constant as any parameter which is not determined by the theory we are using, in which it appears. Okay, so when you write down a theory, so I will come back to that. Then the links, there are links with gravity, and I lead to the equivalence principle, and they are linked with cosmology, and in particular to all these arguments about fine-tuning, naturalness, blah, blah, blah. So yes, why this definition? Well, you write down a theory, you have different objects, and you have numbers that cannot be explained by the theory itself. The only thing you can do is measure them. And well, the reason why you cannot explain them is that there is nothing more fundamental in terms of which you can derive the value of this fundamental constant. I was telling you about the mass of the protons. Unless you know about QCD, you do not ask yourself, can I derive the mass of the proton? You have nothing more fundamental than the proton itself. They have to be assumed constant because you have no equation of evolution for these parameters. And from an experimental point of view, if your theory has been validated by experiment, just the reproducibility of the experiments tells you that these parameters should not vary on time scales which are comparable to the reproducibility of the experiments. So this is the reason why. So now when you write down your theory, in a theory you make a distinction. In field theory, sorry, you have different kind of fields which are dynamicals, and you have a set of parameters which you assume constant. Now when you vary this kind of action, you will get one equation for each field, and you get no equation for these parameters because they are not dynamical parameters. Which means that now if you assume that some of these quantities are dynamical, you will have also to vary the action with respect to this parameter, which means that you will get new equations. So everything will remain consistent if you work at the level of the action because the propagation equation for these fields will include derivative of these quantities, and you will have an equation of evolution for each of these parameters. So there is no trouble to have, nothing about energy conservation. You just have degrees of freedom that you were supposed to be frozen that are not frozen anymore. Okay. The reason why I think it's very important is that also we have to change to think the way we think about fundamental constants. So this is the international system of units. I think this is one of the most beautiful things we have in physics, because not only tell you what are things, it tells you what is a kilogram, what is a meter, what is a second. I think it's very important to know what are these things. And usually, so we know in the international system of units, we have 7 base units, ampere, Kelvin, second, meter, kilogram, candela, and mole. And they have definitions. And from this definition, we are able to measure by different experiments the value of fundamental constants. We put that into textbook with some error bars. But you know, as I told you, like as a general relativist, the only thing I can measure is time. So we would like to reduce everything to a single clock. And what is amazing is that, well, metrologists are coming to this point today because this is a very lively debate in metrology to shift from this picture to this picture, in which you just have a single clock here to define the second, and then all other fundamental constants will be fixed by the fact that you have written in a book the value of the speed of light, the Planck constant, and other fundamental constants. So what you do is you fix the value of fundamental constants, and now the accuracy of your experiments is given by the accuracy of the realization of your kilogram, your meter, and your second. So it changed completely the way you have to think about measurements, but I think it's great because this is exactly what general relativity wants, just a single clock. So you travel with your clock and you can define your international system of units with you, and you all agree on that. That's great. Okay, so again, in terms of ideas, we talked about Newton. Everything was fixed, space-time and fundamental constant. As I told you, in Einstein gravities, they are fixed. This is related to the validity of the equivalence principle. And now when we go to gravity beyond general relativity, they may become dynamical. So one of the questions would be in this theory, why do they vary so little today? So I will not go to all that. I will not talk about. So this is where we stand today. So this is our past light cone. This is our local world line. Let's say the world line of the solar system, and we have many systems. And thanks to your paper of 1999, a lot of people were interested to see whether this claim was correct or not, to get new systems, to go to higher precision, and in 15 years, we have gained many order of magnitude on the constraints, on the variation of fundamental constant from on many time scales. So you have local experiments in the laboratory with atomic clocks, in the solar system with the Oklo phenomenon and the meteorite dating of the solar system. Then population 3 stars is just filling a gap here between a redshift 15 and 30. The quasi-Absorption spectra give information up to a redshift, let's say, of 4. And if we go further in the history of the universe, CMB and BBN can be used to constrain their variation. So I just flashed some recent results, like let's say 2 years, in the past 2 years. You've heard about Planck. So the Planck satellite. So these are the constraints you will get on the fine structure constant and the mass of the electron here. This is what you got with WMAP 9, and this is what you get with Planck. And the interesting point here is that you add a degeneracy, and you break the degeneracy because actually when you work out the all transitions that you need to take into account for describing the recombination, there are some degeneracies which are not seen at low multiples. But when you go to higher multiples, they have a small differences. And because Planck is going to much higher multiples than WMAP, you break this degeneracy. So this is a very nice result of Planck. And you see we get a factor of better than 5 compared to the WMAP constraints. OK, so this is, I told you about, let's say, I don't explain, about stellar physics. So the question is about carbons. Most of you know the Hoyle coincidence for the production of carbons by population 3 stars. And we try to make that more quantitative. So basically try to understand. So this is the nuclear, you start from helium, you want to synthesize beryllium and then carbon, and you have this excited state here. If you change the relative strength of the electromagnetic and nuclear interaction, all these things will move. The ground state will move and the resonance will move. So we try to make a model out of this, and by solving the Schrödinger equation for the helium, beryllium, and carbon, you can compute that by changing the value of alpha and the strength of the nuclear interaction. And then you work with colleagues. So these are colleagues from the University of Geneva who have a code for stellar nucleosynthesis. And you can put your new cross sections in this code, and basically you run that for population 3 stars, so with 0 metallicity of different masses. So this is an example with the 60 solar mass stars. And you see, this is a standard model. You get some carbon and oxygen. And this is what you would like to have for some kind of biological mechanisms to work. But now if the nuclear interaction is stronger, well, actually you will not get any oxygen. You will just get pure carbon. On the other hand, if it's weaker, then first you will synthesize a lot of oxygen and you will have no carbon, and then there will be a kind of runaway and you will produce a lot of magnesium. So you will end up with a magnesium star, almost. Stars that Joe, have we seen some stars like that? No, never. But if one day we discover a magnesium star, we have a model for that. Okay, so this is the same for Big Bang nucleosynthesis. I will not go into the details, but again, you have to change all the constants and see how they change the different nuclear interaction rates. Here it's very complicated because you have to take into account the coupled variation of many constants. What is important, and I will finish on this slide, is that this is what we got in 2006. In 2006, these were the data for helium, deuterium, helium-3, and lithium-7. And you see this was the range of allowed for a variation of this parameter, mass of the electron, binding energy of the deuterium, the difference between mass of the neutron and mass of the proton, and the lifetime of the neutron. And within this window, there was this small patch here where, well, your prediction will be compatible with lithium-7, deuterium, and helium. Okay, it was interesting because the lithium is still, I think, in the cosmological problem. You said that everything is working well. No, there is a problem with the lithium-7. We don't understand why the lithium-7 is not compatible with what we predict from a standard Big Bang nucleosynthesis. So that was in 2006. And then there were better data coming for helium. And you see this error bar has shrunk quite a lot. So it's reversed, sorry, because it's not the same parameter. But this circle was lying here. And you see today it's no more compatible with helium. It tells you also that, well, it's very important to get more and more observation with a higher accuracy, because this kind of model you can try to rule down. So this is basically what I want to say. I don't have any conclusion, so I stop here. Thank you.
Questions? Bernard Carr.
Thanks, Jean-Philippe. I was very interested in your model for the emergence of Lorentz signature, but could you explain in a bit more detail how this works? You're invoking a scalar field, but is the idea that, for example, this transition could occur in the early universe, or is it occurring in different places in space? And if it's true, under what circumstances can the signature be reversed back to what it was?
Okay. So it's not in the early universe because there is no early. Okay? So you start with a purely Euclidean space. So what you get is, then you have to tell what this space is. Maybe this is a compact space with some boundary conditions, and you have all your equations, and you get some kind of configuration for these things. Okay? So this is the first thing. Like the picture I showed. Okay? Then, if on some patch of this configuration space, you have zone in which the gradient is of this scalar field is almost constant. So basically on this patch, you can say that it has a kind of vacuum expectation value, a fixed value. Then you look at the dynamics of the other field in this background. And because of the couplings, an observer that will be in this patch will interpret these fields as if they had a dynamics. So what you have to think, this is the way I try to think about it, is that if that were the case, the whole observable universe should be in such a patch of this big four-dimensional space, which would be pure, in which, from an outside point of view, has no dynamics. Okay? But again, I want to make very clear that this is not something I'm pushing as an idea or I believe in. This is just to try to see how far we can go. And I think this is a very, very nice exercise to see what it costs, to reproduce what we know with purely. Maybe you will see a collision for another patch in which this direction is in another direction. And that's this idea. Maybe like the Big Bang singularity is not a singularity. It's just like a domain wall in this scalar field, in this configuration space.
Sudarsky.
Yes, I'm Daniel Sudarsky. I was also very curious about this model in which you have emergence Lorentz metric. And the question is whether it would be natural for all types of matter, vectors, scalars, fermions, to couple with a unique metric, which is the property of a geometric theory.
Yes. I thought about that. This is we addressed the question in length in the paper, because it's true that, I've hidden a lot of things because it was very short. But in principle, I put a number in front of this interaction term. If I put different numbers for different fields, then they will not propagate in the same Lorentz metric. Then the question is that in standard physics, why are we assuming that they are coupled? I don't talk about gravity, but just let's take Maxwell plus the scalar field. Why do you assume that they are coupled to the same Lorentz metric? It's just because you want to be sure that the equivalence principle is strictly sure. So if tomorrow you see a violation of the equivalence principle at 10 to the minus 13, the first thing that you will do is to take two metrics which will be slightly different. Okay? So this is just an empirical fact. There is nothing that tells you from a fundamental point of view that you need to propagate in the same metric. Okay? So this is a kind of coincidence in some sense. But once you have fixed the numbers, you know, there will not be, it will not be space dependent in this big patch. I mean, the difference will be the same everywhere. So this is a feature of the theory, it's not a local feature. Okay. I don't know whether it answers. Yeah, we can.
Okay, Rafti.
Thank you very much, Jean-Philippe. If I may just make a historical comment that I think is very relevant and supports your thesis. Really, as a group, we were really struck when we started looking at Einstein's models of the cosmos that were written after the discovery of the expansion. He never uses the word effective theory in that sense, but he clearly thinks along those lines. I mean, in almost every case in the first paragraph, first is a discussion of the domain of validity and a lot of questions about whether one can really make this extrapolation. And second, when it comes to matters concerning the singularity, it's very much phrased in terms of the model breaks down simply because the framework on which it's based runs into trouble. And I just think that's really interesting because a lot of historians up to now have always sort of said, well, Einstein, as you know, wrote very little on cosmology after the discovery of the expansion, and was it because he just disliked it? And instead he went on to unified field theory. But of course they missed the connection, and the connection seems to me very much coming out, especially when one looks at manuscripts and things, that he is so unhappy with this sort of effective, particularly when you take general relativity and try to apply it to the universe as a whole. That's one of the things that's driving him towards the unified field theory. I don't know if John would agree with that, but that's certainly the impression we have.
Okay, let's have one more question, then we'll finish on time. Jim Hartle.
Jim Hartle, is your effective gravitational theory that you get by this construction consistent with existing experiment, in particular the spin down of the binary pulsar, which is very sensitive to adding scalar fields because you get monopole radiation, or maybe it's just some toy model that you hope to improve on?
Yeah, okay, so we didn't go as far as a binary pulsar. That's a very, even in general relativity, it's a very difficult computation. But what we checked is that it's compatible with variation of fundamental constant, it's compatible with test of the equivalence principle in the solar system and all tests of general relativity in weak field. That we can test easily because it's perturbation theory.
Okay, including the binary pulsar.
Yes, but it's yes, but you know that you have to take, well, to be very careful about the quadruple formula and so on. It's just purely, I mean, you have to do that with care, which we didn't have time to do. And also, I must admit, like going through such a long computation depends whether, I mean, to which extent you believe in this kind of ideas. So we were more trying to make sense. First, our best problem, I mean, most important problem was how to get Weil and Majorana fermion. It's a very difficult issue, actually, which took us many months to solve. So we find a way to define them, and so now we are more trying to look at issues about, can we, in some sense, invent something that would look like some kind of quantum theory, which I think is probably like the killer for these things before even the binary pulsar.
Thank you.
Could I say, unashamedly self-publicizing, if you're interested in varying constants, there's a paper that went on the archive a week or so ago by a group of us, which is coming out in PhysRev Letters in 2 weeks, that has a new technique for constraining variations of electron-proton mass ratio and tests of the equivalence principle in 10 to the 4, 10 to the 5 Earth gravity fields. And it's using discovery of molecules in the atmospheres of 2 white dwarfs. So this is a test within the solar system, but it's precision of parts in 10 to the 5 because you can simulate the hydrogen spectrum in the very high temperature regime within a laboratory at the Laser Lab in Amsterdam, and so have very high precision comparison with the situation in the Hubble Space Telescope spectrum. But that's an aside. Thank you very much, Jean-Philippe, such a clear exposition. Thank you.